Okay, so we have covered, today we're going to go over Kirchhoff's rules, and so at this point we have covered, we've covered resistance, and we've covered voltage, and we've covered capacitance, and we've covered current, and this is where we begin to bring them all together. And this is how, these are the laws that we use for our circuit analysis, are these Kirchhoff's rules, and Kirchhoff, I go back and forth. So we're going to start with Ohm's law, which is pretty straightforward, and then we're going to talk about batteries and voltage walks. And we've done a few voltage walks, paying attention to going through our circuit and the voltage that when we gain voltage and when we lose voltage for whether we're crossing a resistor or we're crossing a capacitor or something like that. And then we have the two rules, Kirchhoff's two rules. They're the junction rule and the loop rule, and we'll do a couple of example problems. So we start with, and we're going to start with a resistor. And let's see, our current is going in that direction. That's A, that's B. If we go from point A to B, okay, the difference between the voltage on this side of the resistor and the voltage on this side of the resistor, delta V, as A goes to B, okay, is equal to the current times the resistance. However, it's negative because this is a voltage drop, right? We are decreasing the potential that as we go through this resistor. Now, if we were to go the other direction, if here's our current, and we're looking at the voltage change as we go from B into the current over towards A, then our potential will increase, right? So so if we're studying the change in our potential as we go from point B to point A, this becomes a positive change in potential. Okay, if we're going against the flow, okay, imagine something where you drop an object compared to potential energy a little bit. Okay, you drop a ball, okay, it's going to lose potential. It'll gain kinetic energy, but it's going to lose potential. If you lift an object into the sky, you are giving it potential, even though because it's going against the flow of your potential. So, Nick.
So, how?
Okay, write your question down. All right. So, if we throw a battery in here, and it goes from point A to point B, and we want to study its, and it has an EMF. Okay, why do I call it an EMF and not a voltage?
Because that's too big for some.
Because
Wait.
because there's no current traveling through it. It is just the standing potential of the battery. Our change in voltage as we go from A to B here is going to be a positive E. And as we go from B to A, it's going to be a negative E. And the batteries are drawn with a direction to them. Remember, the long end is where is the higher potential is on the long end, and the lower potential is on the small end. Okay, so this would have, a smaller potential down here, and then over here it would have whatever this V naught is here. It would have a, V naught plus EMF over here. All right, so it's going to increase the potential as we go in that direction. All right, so we're going to draw let's draw a sample circuit here, and we're going to have a All right, we've got R1 and R2 and R3, and we're going to have a current that's going this way, and we have, we'll call it an EMF to begin with. Okay. In fact, I'll probably start doing this even when it's wrong to call it an E, just to, because I don't want to keep writing V over and over again and possibly getting it confused with the actual units of voltage now that we have this script E that we can use. Okay. As we go around here, okay, let's take our voltage walk. So we're going to start here on the corner, and our voltage walk goes around in a loop, and there are any number of loops that we can possibly go in. Or actually, there's 1, 2, 3 loops we can go in. Okay, so pay attention to this carefully, please. Here are the walks we can go on. We start here. We will lose some potential here. We'll lose some potential there as we go through the resistor. We come back, we go around, we gain our potential again, and we're back to 0. Okay, so as we go around a loop, okay, the voltage remains the same. All right. Now, if we go through another one, we can choose this way. And wind up here, and we wind up with, you know, whatever we gain in potential here, we lose in potential here. And really, the reason for this is the law of conservation of energy. You can't, as you go through a circuit, the energy, it would make no sense if you go, each time you go through a circuit to the same place, that you're going to have a net gain of energy or even a net loss of energy. The energy can't just go anywhere. Okay, except for the heat energy being released by the resistor. Yes, there's that, but the concept of there being a potential, the potential energy still doesn't get the concept is the law of conservation of energy. Yes, we start to lose it. That's where reality steps in and says, you know, that we are losing heat to our surroundings. But there is a third loop here, and this is where I need you guys to pay close attention. Our current is in general flowing in this direction, like so. That means that in here we have another voltage walk we can take within this parallel resistance group. That as we go this way, we will experience a voltage drop. Okay, here at R3. But if we come back around and go to R2, we start going upstream with the R2, and all of a sudden this becomes a voltage gain because we go the other direction. We're moving against the flow up here. Remember, if we go against the flow, we gain in potential as we go against the resistor. Something over here is going to have a greater potential. Something upstream is going to have a greater potential than something downstream of a resistor. If this is upstream, this is downstream, and we go this way across the resistor, we are going to gain voltage. Therefore, IR3 plus negative IR2 is going to equal 0. That make sense? Okay. This leads us to Kirchhoff's rules. Okay. The first one is the junction rule, and I'm not sure if we talked about this per se, but it should make perfect sense. In fact, both of these rules make total sense.
It's a voltage is 0 in the loop.
Yes. Yeah.
So
We'll formalize that statement here in just a minute. Okay. So the junction rule is this. Okay. Here is a junction. This is where wires connect. Okay, or two conductors connect. If you have a current that goes like this, We'll call this I1, I2, and I3. Okay. You know, I want to reverse the direction of I3. It's going to illustrate better. Sorry, guys. Okay. The current that flows into a junction is equal to the current that flows out of a junction. Okay? Think about plumbing or water. Okay? And you have a T with your pipes. Okay? The water's got to go somewhere. It's either going to go here or it's going to go here. Okay? So I1 well, let me phrase it a different way. The sum of the currents going into a junction are equal to the sum of the currents leaving a junction. Probably the better way to put it. Okay, and we can rewrite this as or the sum of the currents in minus the sum of the currents out equals 0. So up here, what's this going to be? That's going to be I1 minus I2 minus I3 equals 0. Yeah? Okay. Pretty straightforward. Okay. That is in conjunction with the loop rule. Okay, but we've already kind of mentioned the loop rule. The idea of the loop rule is the sum of our potential changes, of our potential differences, equals 0 for a closed loop. In fact, for all closed loops. Regardless of whether there is a battery or an EMF or whatever in the loop, doesn't matter. If it's a loop, you do a voltage walk around the loop, okay, and you've identified what upstream and downstream are. Okay, the total voltage is going to equal 0. So it is now time for a trivial example problem. Then we'll go through a harder one. Question.
So how's that little loop closed?
This one down here.
Yeah.
How is it closed?
Yeah. Can it exist?
There's no switch on it. Is it possible to go? It's not limited to that loop. It's just that it's closed. Is it possible to complete a circuit in that loop? Yes. Closed loop. Okay.
So
If you can make the loop, it is a closed loop. Okay. Not whether it will, it's whether it can. Okay. So here's our example. Okay, given this situation where we have pay close attention here. Okay, this equals 6 volts. We'll call this E1. This battery is going to be 12 volts. Here we have R1 equals 8 ohms. Here we have R2 equals 10 ohms. Okay, I want you to find, find A, we want to find the current, and B, find the power output for each resistor. Okay. So the power for P1, the power for each resistor. All right, so we're going to solve for A. All right, and we're going to take our voltage walk. And here's the beauty of it. It doesn't matter which direction you go, so long as you stay consistent with your voltage drops and your voltage increases. All right, so I'm going to take clockwise as the direction for my current. Okay. So, and let's start over here. So we go around, and whoop, we jump up. We have a positive 6 volts of voltage that we're adding. Then we come down here, and the voltage across this resistor, according to Ohm's law, okay, is going to be a voltage drop of our 8 ohms times our current. Yeah?
So 6-fold minus.
Right, because this is an increase, right? We're going minus small to big, so that's an increase in voltage. We come down here, and all of a sudden a resistor is a decrease in voltage, so it's going to be a minus 8I. Okay. Then we come here, oh look, this is going from big to small, right? This is not a voltage increase. This is actually working in the other direction. This is a voltage decrease. Go in the other direction. Come around, and we get to R2 over here, which is 10. So this is going to be, and this is also a voltage decrease as we go in this direction, right? Yeah? In this direction, it's a decrease. So, according to this battery, that's a decrease. Okay, and that becomes 10, negative 10 times the current. And all of this equals 0. All right, we can actually solve for I here. We can solve for what our current is. So we're going to get negative 6 volts minus 18 I equals 0.
So I is 3. Oh, no, negative 3.
Okay, and so I doesn't equal negative 3.
Wait, is it?
Oh, I'm sorry, positive.
Yeah.
Equals positive 18.
Oh, so it's 1/3.
So our current equals negative 0.33 amps, right? Now, what does the negative mean? Right. I arbitrarily chose clockwise to be the current, right? But, and you can kind of eyeball it by seeing this because you have the battery on the other side, right? It's great. The voltage is greater on the other side of the circuit, and it's going to push. It's really going to push stuff the other way. You can't always eyeball it like this, but you can on this one. This negative means that the current is actually 0.33 amps. Counterclockwise. And that's going to be our current for this one. Okay, it's pretty straightforward. All right, now B, so that was A. B, find the power. Well, power, now that we have the current, power equals I squared R, right? And so we have the current and we have the each resistance, and so it's going to be, it's going to be 1/9 times 10 or 1/9 times 8. 0.33 squared is 1, right? Okay. So that's going to be 1.111 and 0.888 and so on. And so really the whole thing is turning out 2 watts. Okay. That's the easy example. And I think I'll stop there, and because it might take us a little bit while to solve the longer one, so we'll leave that at a 20-minute video and record the second one separately.